Let me just check that we are live. We are live. Let me just check that we are live.
Fantastic. Are you ready to go, Francesco?
Yep.
Lovely. Let me just triple check that. It's good.
We are live.
All right. Yeah, I can see it. Fantastic. Okay. Why don't we get started? So thank you so much, everyone, again for being here this week. I'm very happy to have here today Francesco De Santis, who, please correct me if I'm wrong, but you're still, I think, speaking a last year PhD student at the Politecnico of Torino, correct?
Yeah.
Cool. Awesome. Yeah, and today he's going to be talking about some work that sort of I have a bit of stake in this. I've been involved with same as Pietro, which is the mixture of concept bottleneck experts. So yeah, please take it away, Francesco.
Okay, thank you, Matteo, for the introduction. Okay, in this presentation today, I will show you mixture of concept bottleneck experts, which is a paper that we are going to present at ICML this year. But let's go straight to the point. So as you might already know, concept bottleneck models can be divided into two stages. The first one is related to the prediction of human interpretable variables named concepts. And the second stage instead is the stage in which we use the predicted concepts and a task predictor in order to make the prediction over the target variable. With respect to the vanilla CBM that you can see here, a lot of improvements have been made. So for example, now we have methods that allows us to learn the dependencies and relations among the different concepts in the bottleneck, or maybe learn or establish hierarchies among those concepts. Or for example, there have been a lot of improvements regarding the training of the concept encoder. So now we are not, we do not strictly need the human supervision on the concept variables, but we can use pre-trained models in order to provide supervision. But regarding the task predictor, as researchers, we usually fix the task predictor a priori, and we fix it to very easy and standard expressions, such as linear equations or very simple Boolean expressions. And actually, what I want to prove you today is the fact that by limiting ourselves to set the task predictor to those simple and naive expressions can limit both accuracy and interpretability. And it is also easy to motivate. Why? Because, for example, if we know that the relation, the mapping between the concepts and the target variable is nonlinear, then if we set the task predictor to a linear expression, we might expect a drop in accuracy on the target variable. But also regarding interpretability, we might set the task predictor to a Boolean expression, but then since the interpretability is user dependent, we will never know if the final user will be actually able to understand this expression. So what we did in this paper was to propose what we called a design plane that allows the developer or the researcher to instantiate new task predictors very easily. And let me show you which are the dimensions that we care about in this 2D plane. So the first one is the number of experts. Here, when I'm saying experts, I refer to specific expressions. And these dimensions allows to have a memory of experts or expressions that the task predictor can use in order to make the final prediction on the target variable. And interestingly, the number of experts is related to both accuracy and interpretability, because it is related to accuracy since basically we can decompose, for example, a nonlinear mechanism, a nonlinear mapping into simpler linear expressions. And we can do that by just increasing the number of experts. And it is also related to accuracy because, of course, the larger the memory, the higher the number of experts, and the more expressive the task predictor will be. And the second dimension instead is the functional form. And the functional form actually controls each expression in the memory. So for example, as you can see here, we can now set a linear expression, or Boolean expression, but also a polynomial or anything that we might still find interpretable. And also this dimension obviously is related to both accuracy and interpretability. And the interesting thing about this design plane is the fact that now we can show the human and the task constraints, and according to those constraints, we can define a region within which we can move in order to find not the perfect, but the task predictor that allows to have the best trade-off in terms of accuracy and interpretability. And of course, we can also see that different already existing CBMs occupy different regions or points into this space. But what emerges is the fact that there's a very huge area that has not been explored before. So in order to show that the usefulness of this 2D plane, we also instantiate two new models that explore this area, and we show that actually by instantiating those two new models, we can find task predictors that are at the same time both more accurate and interpretable. So before explaining you more in detail the architectures of the different instantiations we propose, I want to give you a very short probabilistic overview over our framework. So this is the probabilistic graphical model associated to a standard or a vanilla CBM that allows this factorization here. And what changes with respect to our framework is that now we also care about predicting the expression represented by this T here. Most importantly, in our framework, we always constrain the memory to be a finite memory of expressions. Because obviously, if we predict a new expression for each sample, then it will be not possible for the final user to inspect the task predictor, because it will not have any idea of the behavior of the task predictor as long as it does not have the input, the X in this case. Okay, this node T represents an expression tree. And an expression tree is a very useful structure that allows us to associate a tree to an expression. In fact, as you can see here, this expression here is represented by, or can be represented also by this expression tree that we see. So in the expression tree, basically we have that the edges represent the relations among the different quantities or nodes in the graph, and they can be completely learned from scratch. That's what they usually do in symbolic regression. And in our context, we care about the differentiating different nodes. So the first one are the input nodes that in our implementation will be replaced by the concept predictions. Then we have the operator nodes, and we also care about those nodes because maybe as users, we might find certain operators not interpretable. So we would like to have an expression tree that contains only certain types of operators that we can understand. And then we have the parameter nodes that are real numbers that have to be fine-tuned during training. The expression tree is particularly interesting because it allows us to define different constraints on the expression. And for example, here we might want to have an expression tree who has a certain maximum depth, because we know that beyond this maximum depth, we will not be able to actually understand what's happening in the expression. Or for example, as I told you before, we can change the operator set, or we can force a particular structure while learning the other part of the expression tree. Okay, so this is the first instantiation, which is the linear, what we call the linear M-CBE. And basically, this is the simplest instantiation that we have. And actually, what we do is to fix the memory with linear expressions. So now in the memory, the only thing that we want to learn are those parameters theta that represents the weight of the linear expressions. Then the architecture is structured as follows. So we have also in this case the usual concept encoder that makes prediction over the concepts. And then we have a selector that will identify or predict the specific expression according to the input. And in the end, the final prediction is obtained by combining the selected expressions with the predicted concepts that are going to be substituted to the input of the expression. Okay, regarding the other instantiation that we called symbolic M-CBE instead, we wanted to allow more flexibility to the user in order to constrain the expressions that the model is going to learn. Because in the previous case, we forced the model to learn linear expression, but now we want to have to add more flexibility. And the architecture is structured as follows. So first, we have a memory where we set each cell in memory with an MLP. And the first training of the architecture is performed by using those MLPs here. So basically what will happen at the end of the first training is that the selector will learn how to partition the input space, and the MLP will approximate a specific expression that maps a specific region of the input space to the target variable. Okay, after this first stage, what we do is to take each MLP and the associated inputs routed by the selector, and we run a symbolic regression algorithm in order to extract the expression. And now what we can do is to introduce the human constraints. So for example, as I told you before, we can set the maximum depth of the tree, or we can set particular substructures in the tree, or for example, we can set the parameters that we want to use in this expression. Okay, and the last part, in the last training of this architecture, we swap the MLPs with the extracted expressions, the one we extracted from the symbolic regression, and we perform a final fine-tuning in order to fine-tune the remaining parameters in the expression. And then the final prediction is produced by just replacing the input of the selected expression with the concept predictions. Okay, so that's it for the methodological part. Now we'll show you the experimental results. One thing that I want to remark here is that we measured the interpretability by means of two proxy metrics. The first one is intervenability. So how well does the model respond to ground truth interventions? And the second one instead is complexity. Actually, there's not a unified definition of complexity. There are multiple ones. What I'm going to show you is the complexity defined as the total number of nodes in the expression tree. But in the appendix of the paper, you will find also other complexity metrics that we used. So, okay, the first results basically shows the trade-off between accuracy and complexity. So in the x-axis here, what we have is the the complexity computed as the total number of nodes, whereas on the y-axis, we have the error. So for a regression dataset on the top row, we have the mean absolute error, whereas on the bottom figures, we have the error rate, which is computed as 100 minus accuracy. The different points in this plot represent the different instantiation of our models and the CBM baselines. For certain models, you will see multiple points, and this is due to the fact that certain models can be instantiated with a different number of experts, such as the one that we are proposing. The first thing that I want to remark is the fact that the symbolic M-CBE, according to its flexibility and to the to the possibility to learn the symbolic expression from the data is particularly effective on regression tasks. And as you can see here, where the symbolic M-CBE is constantly Pareto optimal, whereas, and you will see it better in the next slide, the linear M-CBE is very robust for classification. And it is interesting also because the fact that the linear M-CBE can have access to multiple expressions allows also to have good performance, good accuracy, without sacrificing too much complexity, also when the bottleneck is incomplete. So as you can see here, the orange cross represents a standard CBM with a linear task predictor, whereas those points here represents different instantiations of the linear M-CBE. Okay, the last thing that is worth noting here is the fact that we found that task predictors using Boolean expressions do not scale very well as the number of concepts grow. And as you can see also here in CUB, sorry. And we think that we are not entirely sure why this happens. We have different hypotheses, and we also have an ablation on the appendix of the paper. But basically what it might happen is that the rule that they learn is a logical end of different concepts. So what it might happen is that as the number of concepts grow, the probability of one concept being wrongly predicted is very high, and that makes the entire rule fall apart. And obviously, okay, this is a little bit maybe less interesting, but for both regression and classification, and you can see it better here, the M-CBEs using just MLPs in memory are almost never the optimal trade-off between accuracy and interpretability. In fact, as you can see, for example, in the regressions, they are constantly Pareto dominated by other models, and this also happens for classification. Or maybe they show lower error, but the cost of using those MLPs is a huge complexity with respect to other models. Okay, then another thing that I want to emphasize is the fact that we force each model to have a finite memory of experts. And this is particularly important because there are certain models, such as LICEM, that basically has a task predictor, which is a linear expression, but it predicts new parameters according to the new samples that are provided. So basically, we cannot know in advance what are going to be the weights predicted by this model without providing a sample to it. The thing that we can try to do is maybe to study the distribution of those weights, but as you can see here, it is much easier for a user to just, for example, by comparing with the probability distribution of linear M-CBE, we just have 2 points. So it's much easier for the final users to inspect the task predictor. Okay, the next result is regarding the intervenability or responsiveness to interventions. And as you can see here, we still, for regression datasets, we can still see that symbolic M-CBE is very responsive to interventions. And this is also motivated by the fact that the expression that it is able to recover is almost identical to the ground truth expression that we use to generate the data. In fact, as you can see here, we have a metric of similarity between two different symbolic expressions. And as you can see, the symbolic M-CBE basically goes to 0. I mean, this was not exactly 0, but very close to 0. And in fact, as we can see here, when we intervene, the error goes basically to 0. And again, the linear M-CBE, on the other hand, is very responsive to interventions for classification tasks. And this can be seen also from all the plots on the different data sets. Okay. Another interesting result is the fact that the symbolic M-CBE, according to its architecture, can be trained into stages. And this allows us to do a first training that does the heavy lifts in training the selector, concept encoder, and the different MLPs. And then we can actually use this model multiple times according to different user needs, because now when the user specifies specific constraints or specific operators or specific expression trees, then we can just rerun the symbolic regression and swap the expression into the memory. Here what we performed was an experiment where we basically trained the M-CBE using MLPs in memory, and then we gradually replaced these MLPs with expressions that were using a wider vocabulary of operators. And obviously, as we might expect, the wider the set of operators, in general, they are more accurate. Okay, this is not always true, because as you can see here on the MOPS dataset, the error raises a bit, but the trend is clear. Okay, and last, I also wanted to show you these, let's say, bonus results that we just have in the appendix. Basically, we also wanted to test the responsiveness to interventions of the different models we instantiated and also the other baselines by perturbing the input. So by pushing the input into an out-of-distribution setting. And we did that by just adding Gaussian noise to the input. And as you can see here, basically, the symbolic M-CBE on the regression datasets is still capable to basically recover almost zero error when we intervene, whereas other models that allows more leakage to pass through the bottleneck are not very effective in recovering performance when we intervene. And this is especially emphasized by the LICEM. And yeah, that's it. The final takeaways that for me are most important, according to the experimental section, is the fact that when we design a CBM, usually we only care about the improving the concept encoder or improving the bottleneck, but we rarely think about improving the task predictor, which instead, as I've already shown you, basically this allows to recover both accuracy, interpretability, and also responsiveness to interventions. And another important thing that is worth noting is that by navigating this 2D design space, basically what we can do is to find the task predictor that is most suitable for us. And yes, then the other two instantiation. So if you want to use something that is very simple to implement, that works very well on classification tasks, then the linear M-CBE has proven to be very effective. If instead you want something that is slightly more complex, that requires a bit more, a longer training, then the symbolic M-CBE is the choice for you. But of course, you have now more flexibility in defining the constraints for the expression trees. And so that's it. Thank you for everything.
Amazing. Thank you so much, Francesco.
Thank you.
Fantastic talk. Do we have any questions from anyone in the audience? Let me see. Also, actually, yeah, Aya, go for it.
So you said like the symbolic M-CBE is more difficult to train than the linear one. So like how, like, for example, how much does it take for like a given data set to train both?
I mean, the problem here is not related to the first training, which more or less takes the same amount of time that it will require to train the linear counterpart. The problem is related to how do you extract the expressions. So, for example, symbolic regression in this case is very effective, but since basically what they do is a greedy search over the space of all possible expressions, this is actually this takes a lot of time. So, for example, in CUB, it took basically near to 20 hours to extract all the expressions for all the possible tasks.
And you did that. You did that for every single classification, like every single class for the CUB.
Yes. Yes, because basically now what you have to do is to, instead of Y, you have either a probability or a logit, and then you have to produce a logit for each of the classes in the target variable.
Okay, and for the linear one, it's just one linear classifier per label, basically.
Yes. In the end, what you end up with is a matrix of weights that is selected.
Okay. So it's like, okay, so that's why it's more. So the mixture of experts at the end of the day is also like you don't constrain every single one, or like so the model just selects the weights that it wants for a given target, so it can use different experts, right? Like your typical MOE or the linear. Okay. Okay, that's my question. Thank you.
You're welcome.
Any other questions for anyone else? Yeah, we do with time. We have time. Okay, maybe I'll go with a couple of questions as well. Sorry, obviously I'm a bit more familiar with this one than other talks that I usually ask questions about. But I guess actually something I was thinking about is, do you ever see a sort of instance where it could be useful to have sort of multiple experts with different complexities within the same model, and also in that instance having the option for the model to choose when to use a more complex expert and only use them when they're more like necessary. So sort of dynamically pick the complexity of an already trained model depending on the sample. So if it can be solved with something simpler, you'll choose that because you could argue that maybe that's more interpretable and so on, rather than something more complex that could be more powerful, but it should only be used in like the most complex cases. Like, do you think that something that could be worth exploring once you've trained all these models, all these experts?
Definitely. I think that is also something that we wrote in the paper, because probably what you can also do is to, as you said, have multiple, expression with different complexities within the memory, and then maybe if you want to select just the least complex one, you can do that. So you will end up with a memory where you have a hierarchy of expressions with different complexities. It is for sure worth exploring. The point for us that on the data sets on which we tested, there was not particular reason to do that. But of course, it's for sure an interesting line of research from here.
Cool. And I guess the maybe a more practical thing, which is like, I think there's some ablations, but if I can remember, but yeah, how important is the number of experts in terms of how difficult is it to fine tune? Because I imagine that's probably the most important sort of aspect of how things work. So do you have any recommendations to how to actually find that number in practice? Because I guess it depends on how you're going to use it. But
yeah, unfortunately, the only thing that I can suggest is to try different instantiation. maybe start with the one expert or just few experts, and then increase gradually the number of experts. As soon as you see that there's an elbow such as in the graph that I'm showing you, then I think that you can also decide to stop and stick with that number of experts that allows you to reduce the error while not introducing additional complexity.
Okay. Yeah, makes sense. Yeah, Giovanni, go ahead.
Hello, can you hear me? Is it?
Yeah.
Okay. No. A follow-up on this. Do you think we can optimize the number of experts, and like during training, like keeping it as a variable you learn, like it was a non-supervised concept or something like that?
Yeah, sure. We could do that. The only problem that I see with that is that dealing with the selector is not so easy, because, for example, what we might want to do is to just set a huge memory, so a lot of experts, and then force the selector to constantly pick just a subset of them. The only problem is that selecting over a huge memory of experts cannot be trivial. So it is also an interesting idea. But I think
try going the other way around, like starting from one expert, and then during training you try increasing it, and once you see there is no value, you try and find the optimum. I don't know whether this is easy to optimize.
Yeah, we could do that, but I think that maybe then it would be very similar to retraining the model from scratch, because, for example, the selector, if you had another expert, then it has to be initialized again, and you have to restart the training of the selector. Otherwise, you will just select one of the experts that you had in the previous run.
Like maybe just to
Thanks.
discuss it in a bit more hand-wavy manner. I think like another way you could do it is if the expert can be parameterized in a way that you could parameterize as a function, like given some input, it generates the parameters of your expert. Then you can maybe do what Giovanni was suggesting, but thinking this almost in a sort of active learning component where you sort of generate experts until your confidence is good enough at inference time. So you train the model that is this expert generator, and then you can keep generating experts at inference until. And now, how you actually train this, I have no idea how easy would it be, but it should be possible. Like it's almost like active feature selection or those things where you sort of select things until you have enough confidence. But in this case, what you're selecting is the experts that you keep generating. But yeah, a lot of things depend for this to work, and I don't know how you actually train it, but it could be doable, maybe.
Yeah. Sure. Yeah, the only problem is that in the end we had to stick to symbolic regression, because we also tried other approaches to extract symbolic expressions from data. But for example, we used also Kolmogorov-Arnold networks, but they are very difficult to train. They do not scale well with the number of inputs, and in general, they extracted expressions that were far more complex with respect to the one extracted from symbolic regression. So in the end, we had to stick to it, and that was the main problem actually. But yes, for sure, there's a way to do what you just said.
Yeah, no, I'm curious as also whether it's worth doing it, just in case, because maybe sometimes maybe could be a bit of an overkill. But I can see it. It goes around the problem of memory and fine tuning the experts, right? So it's just the model has full decision over everything, but I can see a lot of downsides to it as well. So I'm not sure to balance it out. I'm not sure if it's a good idea or not. But worth considering it.
Yeah.
Awesome. Are there any other questions from anyone else? If not, then, well, yeah, thank you so much, Francesco. It was really fun, really amazing, and really good work. And thank you everyone for coming today. I think we're back next week, if I'm correct. Let me just triple check that before I lie to you. We are back next week, so do call me if you have the option. I think Daniel's going to be presenting hyperbolic concept Bottleneck models. So yeah, thank you so much, everyone, and hopefully see you next week.
Thank you. Bye.
Everyone, bye. Bye.